Welcome back to the deep dive. Today we're plunging into a challenge that consistently tests the mettle of DevOps and cloud engineers, especially those of you maybe prepping for high-stakes interviews or, grappling with those real-world scaling nightmares. We're talking about cold starts. Specifically with Java 21 Lambda functions, when you're facing truly massive scale, I mean, picture something like 50,000 requests per second. And this isn't just like a minor annoyance, it's potentially an SLA killer.
Oh, absolutely. It directly threatens your service level agreements. It can cripple user experience, hit vital business metrics. It's serious stuff.
Right. So our mission today is to unpack three powerful strategies to combat this: AWS SnapStart, Provisioned Concurrency, and native compilation. We'll explore how each one works, their inherent trade-offs, and maybe most importantly, how to intelligently combine them for, optimal performance and cost effectiveness when you're staring down that kind of extreme traffic. All right, let's set the stage then. Here's where it gets really interesting. Why are cold starts such a monumental deal, especially for Java 21 Lambdas hitting, say, 50K requests per second? I mean, a single cold start for Java 21 can easily take, what, over 3 seconds?
Easily. Sometimes more, depending on the complexity.
Now imagine that impacting even a fraction of 50,000 requests hitting your system every second. It's not just one cold start here or there. Lambda's concurrent execution model, well, it means you need hundreds, maybe even thousands, of warm containers just to sustain that kind of throughput.
Exactly.
Yeah.
And every single time your function needs to scale out to meet that demand, it triggers more cold starts.
Which leads to this sort of waterfall of latency, right?
Yeah.
Directly hitting the user experience and critically your service level agreements.
Yeah, it's like asking your users to just sit there and wait. Wait for the application to wake up. Not ideal.
Definitely not.
And what's fascinating here is understanding the underlying cause. It's really about the time spent just getting the JVM started up. Then there's all the class loading, initializing dependencies. All of that has to happen from scratch every single time a new execution environment spins up.
So it's not just a minor inconvenience then?
Not at scale, no. At scale, it's a fundamental bottleneck that can completely derail your application's performance goals. It can make even, really robust architectures just crumble under that load.
Okay, let's unpack SnapStart first then. This one feels like AWS kind of heard our collective prayers for Java cold starts, didn't it?
Yeah, you could say that.
Walk us through the magic behind it. How does it actually manage to bypass that entire startup dance we just talked about?
Yeah, SnapStart is actually quite elegant in its approach. What AWS does is take an encrypted snapshot of your fully initialized execution environment after the init phase of your Lambda function completes.
After the init phase, okay.
Right. So when Lambda needs to scale out and provision new instances, instead of starting from absolute scratch, it just restores directly from this pre-warmed snapshot.
So it bypasses the traditional JVM startup.
Completely. And significant parts of class loading and much of the dependency initialization process, too. Think of it like a quick resume from hibernation rather than a full cold boot every single time.
That sounds like a pretty significant leap forward. So what does this actually mean for the raw performance numbers? Give us the juicy details, especially for Java 21, so we can really grasp the impact here.
Yeah, the numbers are compelling, especially when you think about the scale we're discussing. So let's talk percentiles. P50, that's your median half, your requests are faster. P90, 90% or faster. And P99 is pretty much your worst case for almost all users. Without SnapStart, your P50 cold start latency could be around, say, 3,156 milliseconds, 3 seconds plus.
Wow, okay.
But with SnapStart enabled, that drops dramatically. We're talking 1,591 milliseconds.
So nearly halved.
Pretty much. And then if you add priming, where you actually pre-execute critical paths, like maybe warming up database connections during the snapshot creation.
That's clever.
The P50 drops even further to a really remarkable 761 milliseconds, sub-second.
That's huge. What about the higher percentiles, the P90s and P99s?
Similar story. Looking at the P90s, you go from maybe 3,293 milliseconds without SnapStart down to 1,823 with it, and then down to 956 milliseconds with priming added.
Under a second for P99.
Yep. And even at the P99, your worst case scenario, you're seeing a reduction from, let's say, 3,606 milliseconds down to 2,022 milliseconds with just SnapStart, and then all the way down to just 1,200 milliseconds, so 1.2 seconds with Prime.
Wow, that really is a dramatic reduction across the board, taking seconds off. Even for those P99 worst case scenarios, that's a total game changer for user experience at this kind of scale. So beyond just the raw speed increase, what are the other key benefits you get from adopting SnapStart?
Well, one of the biggest advantages, honestly, is zero additional cost.
Really? Zero cost.
Yep. You only pay for the actual execution time, not for storing the snapshot itself or anything like that. Um, there are also typically minimal code changes required in most cases.
So easy to adopt then.
Yeah, generally very easy to adopt for existing functions. It provides automatic scaling, which is crucial for those unpredictable traffic bursts. And that priming capability we mentioned, it allows you to pre-execute critical code paths like database connections during snapshot creation. That ensures your function is, truly ready for business the moment it's invoked from that snapshot.
That sounds almost too good to be true. Tackles a core problem, minimal fuss, no extra cost. But, in the real world, there's always a but, right?
Usually is.
Where does SnapStart maybe fall short? Or what are the scenarios where it's not the complete answer?
You're absolutely right. While it's powerful, it's definitely not perfect for every single scenario. You're still seeing latencies, in the 700 millisecond range, maybe even slightly over a second at the P99, specifically during those scale-out events when a new instance is restored.
Okay, so still some latency, just much less.
Exactly. And that might not meet extremely stringent, like sub-100 meters latency requirements for certain critical applications.
Mm-hmm.
Also, something to keep in mind. These snapshots expire after 14 days for idle functions. It means they'll require reinitialization if your function hasn't been invoked for 2 weeks. Now, for high-scale continuous workloads like our 50K RPS example, this is probably less of a concern.
Right, it'll stay fresh.
Exactly. But crucially, and this is a big one, you cannot combine SnapStart with provisioned concurrency on the same function version or alias.
Oh, interesting, okay.
That's a significant point when we start thinking about blending strategies later on.
That last point about not being able to combine them on the same version leads us perfectly into our next solution, provisioned concurrency. Now, this has been a known quantity in the Lambda world for a while.
It has.
So how does its core architecture differ from SnapStart, and how does it tackle cold starts?
Provisioned concurrency, it approaches the problem fundamentally differently. Instead of waiting for a snapshot restore, it proactively pre-creates and maintains a set number of warm execution environments before any traffic even arrives.
Okay, so they're just sitting there ready.
Exactly. They're pre-warmed, pre-initialized, which means that every single invocation that hits one of these pre-warmed containers becomes a warm start by default.
No cold start possible for those requests.
Correct. The JVM, all your dependencies, your initialization code, it's all already running and ready to process requests instantly. It's kind of like having a dedicated fleet of taxis just waiting at the airport rather than calling one when your plane lands.
Okay, so guaranteed warm starts. That really is the dream for consistent performance, isn't it?
It is.
But there's always a trade-off, especially when we talk about cost for something as demanding as 50,000 requests per second. What are the performance characteristics we can really expect here? And what's the financial implication look like for a workload of that magnitude?
Well, in terms of performance, you can expect consistently double-digit millisecond response times. Like very fast, very consistent.
Double digits, wow.
Yeah. There's virtually no initialization latency during traffic spikes because, again, the environments are already running and primed. This leads to incredibly predictable scaling since your environments are pre-allocated and just waiting.
Okay, sounds great. Now, the cost.
Yes, the cost. For 50,000 requests per second, especially if it's sustained high throughput, you might need anywhere from, say, 200 to maybe 500 provisioned concurrent executions constantly running.
Okay, that's a lot of instances.
It is, and approximately $13 per month per always warm instance. Well, you can do the math. That can quickly translate to a pretty significant cost.
We're talking thousands per month.
Yeah, you're looking at roughly $2,600 to maybe $6,500 per month just for the concurrency reservation itself. And that's before you even factor in the actual execution costs for the request being processed.
Oof, okay.
It's definitely a premium you pay for that predictability and guaranteed warmth.
Right. That's a significant financial commitment just for that foundational layer of warm instances. So considering this potentially substantial cost, when is provisioned concurrency the strategic, maybe even non-negotiable choice? Why wouldn't everyone just use this if they have high traffic?
That's an excellent question. Because of the cost, it's really ideal for specific use cases. Think latency critical APIs, where sub 100 millisecond response times are absolutely mandatory.
Like real-time bidding or finance?
Exactly. Real-time bidding systems, critical financial transactions, things like that.
Yeah.
It also really shines with predictable traffic patterns where you can reliably forecast your concurrency needs.
Like a batch job or known peaks?
Yeah, maybe a fixed batch processing window or a well-understood peak hour for an e-commerce site. You can provision for that peak and then maybe scale it down.
Yeah.
And of course, for any truly customer-facing application where even a minor cold start delay would directly create a poor user experience and potentially impact conversion rates or satisfaction.
So it's about paying for that guaranteed responsiveness when it absolutely matters most.
Precisely.
Now let's shift gears and talk about taking performance to the absolute extreme with native compilation, specifically using GraalVM native images. This sounds like a complete paradigm shift from the traditional JVM approach.
It really is.
How does this manage to eliminate cold starts? And what kind of gains are we really talking about here? Is it even better than provisioned concurrency?
In terms of cold start time, yes. This truly is the performance frontier for that initial startup. Ahead of time, or AOT, compilation with GraalVM, allows you to produce these self-contained native executables. These completely eliminate the JVM startup overhead because, well, there's no JVM to boot up and warm up in the first place.
No JVM at all.
Nope. These images run on Lambda's custom runtime, like provided.al2, and they achieve cold starts typically around 310 milliseconds.
Whoa, 310 milliseconds.
Yeah, that's like a 10x improvement over standard Java runtimes without SnapStart. It's like pre-compiling your entire application into a single, highly optimized binary that's just ready to execute almost instantly.
That sounds incredibly fast. Almost seems like the ultimate silver bullet for cold starts. But usually, performance like that comes with, let's just say, significant trade-offs.
You hit the nail on the head.
Often in development complexity or ecosystem compatibility, right?
Yeah.
What are the technical complexities and challenges involved when we decide to go down the native compilation path?
Yeah, you're absolutely right. There are significant trade-offs to weigh carefully. On the pros side, like we said, you get the fastest cold starts, often sub 500 meters, sometimes around that 300 meters mark. You typically get a lower memory footprint, too, which can save on costs.
Lower memory, okay.
And you get truly deterministic performance, no JVM warm-up needed after the initial start. However, the cons are substantial.
I figured. Lay it on me.
You'll need a much more complex build pipeline. You have to incorporate the GraalVM toolchain, which, could be a steep learning curve for teens not familiar with it.
Right. New tools, new processes.
Exactly.
Yeah.
You'll also see larger deployment packages, often 50 to over 100 megabytes, compared to maybe smaller JRs.
Deployment size could be an issue.
It can be. Then there's limited support for reflection or other dynamic Java features, which are pretty common in the ecosystem. This means you might actually have to re-architect parts of your application or provide complex configuration.
So library compatibility is a big one.
Huge. And related to that, there's significantly increased debugging complexity, especially in production environments. It's just harder to introspect a native binary than a running JVM.
Okay, so faster starts, but more headaches potentially during development and ops.
That's a fair summary. And when it comes to implementation, you really need to think carefully about framework compatibility. Frameworks like Spring Boot, Quarkus, Micronaut, they offer pretty good native compilation support now. But many other standard Java libraries might require specific configuration hints to work correctly with GraalVM, or they simply might not be compatible at all yet.
So you might be locked out of using certain libraries.
Potentially, or you'll spend a lot of time configuring them. There's also a considerable CI/CD overhead. Native compilation isn't instant. It can add anywhere from 5 to maybe 15 minutes, sometimes more, to your build times.
Ouch. Slower builds.
Yep. And you'll encounter runtime limitations too. Things like dynamic proxy generation, heavy reflection use, certain serialization patterns. They may need special handling using specific GraalVM features, or they might just force you to find alternative approaches in your code.
Okay, definitely not a free lunch then. A lot to consider there.
Absolutely.
So we've covered the 3 heavy hitters for cold start mitigation now. SnapStart, provisioned concurrency, and native compilation. Let's bring it back to our scenario. A demanding workload. 50,000 requests per second on Java 21. Which one should we pick? Or, based on everything we've discussed, is there a smarter way to maybe combine them, given their individual strengths and weaknesses?
This is where the real strategic thinking comes into play. For these massive 50K RPS Java 21 workloads, it's almost never about picking just one. It's about intelligently combining their superpowers.
A hybrid approach.
Exactly. The recommended winning strategy is very often a hybrid approach.
Get a cup.
Here's how you might structure it. Use provisioned concurrency to handle your predictable baseline traffic.
Okay, the bulk of the load.
Right. Let's say that covers 70% of your peak load. Maybe that's 35,000 requests per second worth of pre-warmed instantly responsive containers. This gives you that consistent low latency performance for your core demand.
Makes sense. What about the rest? The bursts?
Then for the overflow, the other 30%, or any unpredictable burst capacity during spikes, you layer in SnapStart, ideally with priming enabled, on the same function.
Ah, okay. So you can use them together, just not on the exact same invocation mechanism.
Precisely. Requests first try to hit the provisioned instances. If those are all busy, Lambda automatically scales out using the SnapStart-enabled version for the overflow.
That's clever. Best of both worlds.
Pretty much, you get consistent low latency for the sustained load via provisioned concurrency, and then efficient, faster scale-out for the unpredictable bursts via SnapStart. Crucially, without having to over-provision and pay for concurrency you might not always need.
So you're building a robust base layer and then adding a dynamic, cost-effective burst layer on top.
That's the idea. And to optimize costs, of course, you'd need to continuously monitor your CloudWatch metrics, things like provision concurrency utilization.
Right, to right-size that baseline.
Exactly. You want to right-size your provision capacity based on actual traffic patterns. You set your provision concurrency count on a function alias or version, and then you just enable SnapStart on that same function definition. Lambda handles the routing.
Okay, that makes a lot of sense as a robust architecture for high scale. When then would native compilation be the absolute go-to? Given its complexity, it must be for really specific use cases, right?
Yeah, native compilation definitely remains a specialized tool. It's for those scenarios where its trade-offs are demonstrably worth the extreme performance gains.
Such as?
Well, when you have truly extreme latency requirements, where even the SnapStart recovery times aren't good enough, and sub-200 millisecond cold starts are absolutely non-negotiable.
Okay, ultra-low latency needs.
Right. Think truly real-time, critical user-facing interactions where every millisecond genuinely counts. It can also be strategic, maybe counterintuitively, for highly cost-sensitive workloads, where the economics of keeping provision concurrency warm just don't make sense. Maybe it's used very infrequently, but needs to be super fast on that first hit.
Interesting cost angle there.
And finally, it's often ideal for simpler microservices. Things with fewer, well-behaved dependencies that compile cleanly to native images without extensive configuration headaches. Usually smaller, purpose-built functions fit this mold best.
That makes perfect sense. Okay, so we've designed this robust hybrid strategy, or maybe we've chosen native for a specific niche, but you don't just deploy it and walk away, right? Especially at 50K RPS.
Oh, absolutely not. Setting it up is just the beginning.
What about monitoring and continued optimization once these strategies are actually in place?
Yeah, this is where the ongoing engineering discipline really comes in. You must continuously track key metrics. You want your cold start frequency, even with SnapStart handling bursts, to be ideally less than 1% of total invocations once things are scaled appropriately.
Keep cold starts rare. Okay.
Your initialization duration, especially the time it takes SnapStart to restore and maybe prime, should ideally target under 500 milliseconds to ensure that initial burst is handled efficiently.
Monitor that init time.
Yeah. And for provision concurrency, you really want to monitor its utilization. Aim for somewhere between 80% and 90% utilization to avoid wasting money on idle warm instances, but still have a little buffer.
Find that sweet spot.
Exactly. For tuning, there are other things too. For standard Java runtimes, even with SnapStart, consider enabling tiered compilation level 1. It's a JVM optimization that can speed up code execution by intelligently compiling frequently used paths faster, potentially reducing cold start times further.
Tiered compilation, okay.
Ensure your priming strategies for SnapStart are effective. Do they really initialize those database connections or warm up critical caches or code paths? Because what good is a pre-warm snapshot if the first thing it does is hit a cold database connection anyway?
Good point. Prime, effectively.
And remember, sometimes just giving Lambda more memory allocation can actually reduce initialization time, because Lambda often provisions CPU power proportionally to memory. So don't be afraid to experiment with memory settings. It might seem counterintuitive for cost, but faster init might be worth it.
Right, more memory can mean faster CPU, faster starts, lots to keep tweaking.
Always. Optimization is a continuous process at this scale.
Well, this deep dive has truly shown us that for high-scale Java Lambda functions, there's definitely no single magic bullet for cold starts. It's certainly more nuanced than just picking one solution off the shelf.
Yeah, I think the key insight here really is that modern high-performance Lambda architectures often leverage multiple cold start mitigation strategies in concert.
Blending them.
Exactly. You blend them intelligently to optimize for both performance and cost across different traffic patterns and requirements. It's about layering these powerful tools, provisioned concurrency, SnapStart, maybe even native, for specific parts to meet your specific needs, and crucially, avoid hitting those painful SLA walls.
Transforms it from an intractable problem into more of an engineering challenge with clear, effective solutions available.
Well put.
So what does this all mean for you, the listener? Hopefully you now have a much more comprehensive understanding of the top strategies to combat Java cold starts at scale. You should feel ready to apply this knowledge. Whether you're architecting cutting-edge serverless solutions from scratch, optimizing existing ones, or maybe just acing that next technical interview with confidence. That's all for this topic. Stay tuned for the next deep dive.